Hi, and welcome everybody to our wind blade recycling project. This is an IMSC capstone project by Iowa State University. My name is Jan Dentis.
I'm Jake Drobnik.
John Gregg.
AC Sutton.
And Abigail Wadsworth.
The agenda for today is to go over our problem statement, objectives, solutions, economic impact analysis, route optimization, value stream map, environmental impact analysis, and finally our conclusion. This project was developed as a plan to enter the wind turbine blade recycling industry. The need for this project was brought to us by our contracting company, which identified an increasing number of decommissioned blades yearly in the United States. And to attend this necessity, a blade recycling process was developed. Our team's responsibility was to come up with a strategy for shredding and transporting material to our points of interest. Our objectives were to minimize time and cost to deconstruct the blades at different sites, to efficiently transport section pieces to be shredded and post-processed, and to reduce the carbon footprint through transportation solutions. The team's solution to the problem presented involved the following: cutting and sectioning of the blades on the work sites, transporting section pieces via flatbed trucks to the shredding facility, and trucking shredded material to the post-processing facility and the final product obtained in that point.
For the economic impact, we started by calculating the machinery, labor, and transportation costs for one blade. Machinery includes costs for cutting blades into segments and then segments into shreds. Labor includes costs for 4 operators at the wind farm location and 2 operators at shredding location. Transportation includes costs for both types of transportation for segments and shreds. Next, we calculated an ROI of 39%, which includes the initial buying of the machines for cutting and shredding blades, the investment cost for the finishing facility, and profit. Operation cost was then calculated using a 1.5 megawatt turbine equaling 3 blades and using the average distance from the QGIS data. In table above, it represents where the costs are being allocated between location and transportation, with 19.47% costs being in transportation and 80.53% at location.
Next, we used QGIS, an open source graphical information system software, to map out the existing turbines in the states of interest, these states being Iowa, Illinois, Minnesota, and Wisconsin. This data we imported included the United States Geographical Survey, wind turbine database, U.S. primary roads, and the roads of Illinois, Iowa, Wisconsin, and Minnesota. These turbines from 2012 or older were the ones we're interested in our project, as these would be candidates for recycling in the nearest future. With this program, optimal routes, as you might see on a GPS program, were then calculated from each turbine to our centralized locations. This data was then compiled and used for our various calculations down the line. An example here shows the different types of maps and the different types of routing through the state of Iowa. As you can see, different routes are calculated from the shortest possible path on the primary roads and the secondary roads within these states to the facilities, and then from those facilities to the next place.
Next, we have a value stream map showing an overall layout of the process that was selected as a recommendation. It starts with trucks coming to our cutting site, and then we go into cutting the blades, which is a value-added process time. From there, we load the blade sections and transport them, then needing unloading and shredding, which shredding is also a value-added process time, to loading those shreds and taking them to a post-process facility. Time is divided between value-added and non-value-added, which would include tasks such as shredding and cutting for value-added, and non-value-added is transportation and loading.
For the environmental impact, our team utilized Carbon Footprint, a tool dedicated to finding the CO2e emissions of different projects. For this, we were focused on selecting the economically and environmentally viable solution for the project. In the process, we focused on the fuel consumption and the metric tons of CO2e produced, and in looking at all of the options, we looked at reducing the transportation to mitigate that emission and fuel consumption. Here on the bottom, we can see the option 1 shredding facility with all of the processes, fuel consumption, and metric tons of CO2e emissions laid out. And on the next slide, we see the breakdown of all of this. And here we can see that the trucking has the greatest impact on the process as a whole. And after mitigating the transportation from the other options, this was our best solution, and this can be mitigated further by our company. In conclusion, our process is focused on adding an alternative shredding facility separate from the recycling facility, resulting in lower transportation costs. We'd also focused on the shredding facility having a lower fuel consumption from the 460.5 gallons, or to the 460.5 gallons and 4.39 metric tons of CO2e emissions. We also focused on the shredding facility being located where the highest wind turbine densities are located to increase the truck capacity. The total value-added time is 202.5 minutes, and the total non-value-added time is 500 minutes for the value stream map. And the estimated ROI for the project is 39%. The transportation costs are 19.47% of the total cost, and the location costs are 80.53% of the total cost. Thank you for watching.